Good morning, class. Today we're going to start talking about rotation. Or just spinning, motion, circular motion, rotation around an axis. Okay? So rotational motion is really just an extension of Newton's three laws, which we've already seen. But it is not quite as intuitive as Newton's three laws that we've already seen for translational motion. So rotational motion has some extra features to it which most of us haven't developed the physical intuition to understand. So, but we're going to work on that. So, but let me give you a demo of that first. So, for example, this weekend I'm going on a trip to a conference. And let's say I'm going to bring my suitcase with me. And being environmentally conscious, I'm going to power my laptop on that plane with a flywheel. So next Tuesday, we're going to be talking about flywheels as a way of storing energy. It's an alternative to batteries. Okay? So we'll talk about that in more detail next week. But let's take a look at that right now. So I'm just going to use my little motor here and spin up my flywheel. So I'm doing work on this wheel, I'm getting it spinning, I'm putting energy into it. This is kinetic energy, which we'll be talking about in this chapter. It's rotational kinetic energy. And we can get this energy back out of this by using some electromagnetic techniques we'll talk about later in the semester. But right now, we just got to know that it's storing energy. I'm going to use this on my laptop. Okay, we got this thing spinning up pretty fast now. So I'm all ready to go. I've got my batteries charged, my flywheel's charged. I'm going to the airport. Okay, so far so good. And the motion of this flywheel, even though we can't see it, is having a big effect on the motion of this suitcase. So let me show you. So we're walking along, no problems. Okay, and then I turn. Okay, if I turn back the other way, you'll see that my suitcase is about to push me over. Okay. Should have got this spinning a little faster. Okay. But every time I try to turn, ow, it's actually dragging me around in a circle. The flywheel is having a really major effect. So it's not intuitive why this thing's spinning around in this suitcase is going to affect not only the motion of me, but the motion of the suitcase itself, right? The suitcase, every time I try to turn it, goes lifting up in the air. If I try to turn it really fast, see, that's not from me spinning, that's from the suitcase itself going up. Okay, rotational motion, it's not very intuitive. But we're going to be working on that, so, and trying to get that intuition back built up a little bit. So let's start making some definitions about rotational motion, and then we will turn to some of the dynamics. Okay, so here's a top. Key example of a spinning object. Okay, the first thing we want to talk about is the rotational position. Remember when we were talking about objects, Newton's first law says that when they're at rest, they want to stay at rest. When they're in motion, they want to stay in motion unless they're acted on by outside force. So we're going to look at that law, but in terms of rotational motion instead of translational motion. And the first thing we need to do is define the rotational position. Okay? And to do that, we're just going to pick a direction. And let's say that this is the starting position at our top. And then the rotational position, we're gonna talk about the rotation angle around its axis. So let's define, I'll use this to show the axis of rotation here. Okay. And so our top is going to be spinning around this axis, up and down through the table. And our rotational position is just we're going to say this is the rest position of this top. Okay? If we turn it 90 degrees, then we're at a 90-degree rotation angle, 180 degrees. Okay? And likewise, we can go around to 270, 360. So the rotation angle is just what we define relative to a rest position, the angle that this has been rotated around the axis of rotation. Okay? Same way we could define here, right? Let's say we're rotating this around its axis in this direction, right? 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees, on just like that. Okay, so that is the rotational position, or the rotation angle. Okay. And that is just the angular position of the object that we're looking at. Okay, and it's defined relative to some starting angle that we are basically free to define. Okay? So let's start this top spinning. So we got a good example of a rotating object. Okay, this is a pretty heavy top compared to most toys, so I'm going to try to be a little careful here with this. I need to get a good hold on this. Okay, one thing we know intuitively about rotation from playing with toys like this when we were kids is that once we get this top spinning, it is not going to want to fall over. It's going to want to stay up. Ooh, there we go. You guys hear that? It's like a car, doesn't it? Okay, so we've got the top spinning. We're going to find out next week that what we've given it is angular momentum. And as it's spinning, it wants to stay spinning. Okay. Let's notice a couple things about this. Okay. First off, I've got this spinning around the axis. Okay. And there is a unique direction for this object, okay, which is every part of this top is spinning. Actually, it's spinning in this direction. Every part of this top is spinning in a circle around an axis, which is defined up and down through this table in the up and down direction. Okay. We're going to call this the axis of rotation. So every point of this object is spinning around that. Okay. And it defines a unique direction for this. So let's define that. Axis of rotation, it's the unique direction for an object that's spinning. And if we draw that top, let me see. Here's our top. Okay. Not a great top, okay, but there's our top. Okay. Every point of that is spinning in a circle, so we can, let's imagine that it's spinning around in this direction. Okay. So it's circulating around in a circle there. And the axis of rotation is just running right down the center of it. So this is the line in which every point of that top is spinning in a circle around that point, around that line. Okay? Okay, so another thing to note about this is that the object could be spinning either clockwise or counterclockwise around that line. Okay? So we differentiate those because it's important to know when an object is spinning, whether it's spinning clockwise or counterclockwise. So that's a difference in the angular motion. So we're going to define a direction of rotation which differs whether the object is spinning clockwise or counterclockwise around that axis. And we can call this the spin. And this is defined using what we call the right-hand rule. Okay. And let me show you what that is. Okay, here is our top. Okay. And let's say for this first example, we're going to have it spinning around in this direction. So this is the direction it is spinning. Okay. So that means if we're looking down from the top here, so from the top, this looks like, or from above, this is counterclockwise. Okay. And we're going to define a direction for that, okay, using our right hands. Okay. This might feel a little bit biased if you got a left hand, but this is great in exams because right-handed people have to use their right hands when you can be writing, okay, doing your problems. So we use a right-hand rule, which is that we just curl our fingers into the direction that it's rotating. So in this case, it's rotating around in this direction. And our thumbs are pointing in the direction we define as the spin for the object. Okay? So it's rotating in this direction, and the spin is defined along the axis of rotation in the direction that your thumb is pointing. Okay? If you use your left hand for that, you get the opposite direction. Does not change the physics at all. We just use this as a convention. So counterclockwise from above, okay, defines a spin that's pointing in the upwards direction. Okay, likewise, if we take the same object and spin it in the opposite direction, so using our right-hand rule, okay, we roll our fingers into the direction that it's rotating, and the spin would be defined in the downwards direction. So even if they are rotating with the same number of revolutions per second, they have opposite spins because they are opposite. One's rotating clockwise and the other one's rotating counterclockwise. Okay, so that is the direction. That is just convention. We are going to need that when we're talking about velocities and accelerations. Okay, we need to define a direction that this thing is rotating, and that is just a convenient way to do that. Okay? And we define it along the axis just because, if you think about this, our top steer is still spinning. You can see that every point is moving in a circle. So there's not a unique direction that any point is moving in, but there is a unique direction along the axis, which is every point is moving around that axis. Okay? So that is just a convenient notation for defining the rotation and the spin for an object. Okay, so that thing is spinning, and we know intuitively that it could be spinning slowly or it could be spinning very quickly. Okay? Let's define our terms for that. There's two ways to define how quickly an object is rotating. Okay, the first one is the frequency. Okay, and this is the one that we use in common language mostly. So that's just the number of rotations, so full rotations per time. Okay. And the common unit we use for that is usually revolutions per minute. So when you talk about, which is RPMs. So when we talk about how quickly our gears are spinning or how quickly our record players are spinning or our CD players, we usually talk RPMs, revolutions per minute. Right? The other one, which is what we use more in physics, because it's a closer analogy to translational velocity, is angular velocity. And instead of full rotations per time, it's how many degrees or what angle this thing is rotated for each second. Okay? So it is the angle rotated per second. Okay? And if you know one, it's pretty easy to convert to the other, right? We know that one full rotation of an object is 360 degrees. Or if you're working in radians, like physicists usually do, 360 degrees is 2 pi, okay, going around in a circle once. Okay? I don't want to get fixated on that too much, the units there, but it's pretty easy to differentiate between them. Okay? A very key point here is that angular velocity, just like regular velocity, has a magnitude and a direction. And the direction for angular velocity is the same as we just defined for spin. Okay, so the angular velocity is the same as we defined for spin. So if we went back to these two diagrams over here, we would say this one has an angular velocity pointing upwards in the direction of spin, and this one has its angular velocity pointing downwards, okay, just for our convention. I think this is slowed down enough I can move this. My daughter would love this suitcase, by the way. Big and pink. Okay, so finally, one more analogy with translational motion. As we've been talking, this top has been slowing down. The fact it's been slowing down means that its angular velocity has been changing. And so that means it's been undergoing an angular acceleration, right? Its rotations per minute has been slowing down. And that's because of, ultimately, from friction here with the surface, which is applying a force which is slowing it down. And so it's been undergoing deceleration or angular acceleration in the negative direction, which is slowing it down. Whoa! As I speak. He didn't like me talking about it. Okay, that thing's always scary. This is heavy enough to remove a head. Okay, so let's just draw a picture of that. Very intuitive if you think about analogies with translational motion we've already seen. Here is our top. We had an angular velocity. Let's draw it in this direction. Pointing upwards. So from the right-hand rule, if you want to think about which direction it's rotating, that means it was rotating around in that direction, so into the board on the right. Okay. But as it was sitting there, it was slowing down. So the spin was slowing down, which means it was undergoing an angular acceleration. And from our analogy with translational motion, we know that if it's slowing down, the angular acceleration is decreasing the angular velocity, which means, in that case, our angular acceleration was directed opposite the direction of the angular velocity. So it was slowing it down. So it was slowing the rotation. Okay. Likewise, when I was using the spinner to spin it up, I was also imparting angular acceleration, but it was in the same direction as the angular velocity because it was speeding up the spin. Okay, so we have seen a lot of terms here so far this morning, which sound an awful lot like the same terms we were using for translational motion. And there's a reason for that. It's because we are not, when we're talking about rotational motion, we are not recreating any new fundamental laws. We are just using Newton's laws and applying them in the specific case where we're talking about stuff moving in circles instead of stuff moving in straight lines, okay? But still fundamentally the same laws. And so there are a lot of analogies we can do directly to get a better feeling for rotational motion. The first is, let me just list some of the quantities we studied for translational motion, and we'll look at their direct analogies for rotation. Okay, so these are, let me draw a little arrow going back and forth to show that these are just the analogous quantities between the two. Okay, the first one is for translation. We had position. For rotation, we've got angular position or angular rotation. Same thing. How far have you rotated that object? For translation, we had velocity. Remember, velocity had a magnitude and a direction. Okay. Same thing for angular velocity. How fast something is spinning. Okay. We had acceleration. And we've already seen angular acceleration. Which causes the object to spin faster or slower. Okay. And then two more quantities here, which we're going to talk about today. For translational motion, we had mass. Remember, mass is the measure of how hard it is to start an object accelerating, so how far it is to start it moving or to slow it down. For rotational motion, we're going to define a rotational mass. This is the same thing, if you've ever had any physics before, as the moment of inertia. Okay, two names for the same quantity, and this is going to be our measure of how hard it is to start an object rotating. And then the last quantity, which was really the focus of Newton's three laws, right? Forces, how forces make objects move. And our direct analogy for angular motion is going to be called torque. Okay. And we'll be defining that more today. Okay. So when you're thinking about rotational motion, basically, just about anything you could say about translational motion in terms of these quantities, you can say the exact same thing about rotational motion if you just plug in these words instead of those words. Okay? And they undergo the same exact type of laws in motion. Okay, so given that, we can actually come up with Newton's three laws for rotational motion. Immediately, just keeping in mind that anywhere we're talking about the force for translational motion, now for angular motion we're going to talk about torque, okay? How hard it is to start an object accelerating, rotating. Okay, so let's just write down very short form Newton's three laws for rotational motion. And then we'll come back and define exactly what a torque is and exactly what our rotational masses. Okay, so Newton's 3 laws. This is the remix version for rotation. Okay, so first one, easy. An object that's spinning stays spinning. An object that's not spinning stays not spinning, right? Unless it is acted on by an unbalanced torque. Okay? We can also say that objects remain with a constant spinning motion unless acted on by an unbalanced torque. We already saw a pretty good example of that with this top. You saw that it stayed spinning for a very long time, right, while we were talking. The only torque that was acting on it in any sizable manner was the friction with the table, right, which we'll talk about a little bit more. Okay, the second of Newton's laws. Remember, for translational motion, that was basically the law that the acceleration was proportional to the force, inversely proportional to the mass. So when you apply an unbalanced force on an object, its acceleration depended on the mass of the object. The larger the mass, the smaller the acceleration. Right? The same holds for rotational motion. Okay, so in long words, it's that any unbalanced torque will impart an angular acceleration, and the larger the rotational mass, the smaller the angular acceleration. Okay. In our equation form, that just tells us that angular acceleration of an object would be equal to the unbalanced torque. So it's proportional to the unbalanced torque. And it's inversely proportional to the rotational mass. So the larger the rotational mass of an object, the harder it is to get it to start spinning. Right? So exact same concept as translational motion. We have not defined what rotational mass is yet, but we will in just a couple minutes. And finally, Newton's third law, remember, was the law of action, or is the law of action-reaction. Forces never appear in nature alone. They always appear in action-reaction pairs. Same thing for rotational motion, which is torques always appear in action-reaction pairs. Okay, another way of saying that is if you try to rotate an object, that object will try to rotate you right back. Right? It will apply an equal force back on you that you apply to it. Torques always appear in pairs. Okay, so let's now define a little detail what we mean by torque. Okay, we've been using that word so far this morning quite a bit. But we haven't really defined it. So let's define exactly what we mean by the torque. So the torque is a force acting on an object that is trying to rotate that object. Okay. But we need to add another concept from what we did for translational motion, which is the idea of a lever arm. So in short form, torque is a force with a lever arm. We're going to define what a lever arm is as well in just a second. Okay. But a torque needs to be, in order to rotate an object, you need a torque that is acting with a displacement from the axis of rotation, which is what we call a lever arm. Okay, so this is actually something that you know intuitively, okay, but let's work on that just a little bit. Okay. I could do it first with a meter stick. Okay. If I asked you to, let's say this meter stick is going to be trapped down on this end, so we're going to pick it up and rotating it. Okay, so let me put the blocks here. Okay, if I asked you just to pick up that end, okay, this motion is a rotation. We're rotating this around this axis, so here's our axis of rotation. We're lifting it up, so it's rotating. Okay? So if I asked you to pick that up, I think intuitively most of you would come and grab this end and rotate it from the far end, far from the axis of rotation. If you try to do the exact same thing by picking it up here, okay, it's really, really hard. Okay? It's much harder to pick it up from this end than it is to pick it up from this end. Okay? And that's because in order to rotate an object, we need a force. This is my force lifting it up. Okay? And we need what's called a lever arm, which is a distance from the axis of rotation. And the longer the lever arm it is, the easier it is to rotate an object. The everyday example of that are doors. Okay? This door doesn't have a doorknob, but if it did, we know that doorknob would be over on this side, right? The hinges are over here along this side. So when we're opening that door, we are imparting a rotation to that door. Okay? And we're imparting that rotation around our axis of rotation, which is the hinges on this side. And the doorknob is always, unless you're in a real fancy place, not so bright place, the doorknob is on the far side of the door, okay, because it's much easier to push the door open from the side opposite the hinges than it is if you tried to push that door from this side. Okay. You require a lot more force, more than I can apply, to open the door from the hinges side than you would from the far side of the door. You even need a lot more force than if you're just trying to open it from the middle. Okay. And naturally, you guys know this. Okay. When you go to open a door, you don't go to the hinge side and start pushing on it, right? You go to the doorknob side and start pushing on it to open it up. That is just an example of a force being acted on with a lever arm, which is what we define as a torque. So let me draw a picture of that. Here is our door. Here are the hinges, which are defining the axis of rotation. Okay. The doorknobs are always opposite that. Okay. When we're opening the door, we're applying a force here. This is the force from our hand pushing on the door. Okay. And that force is acting at a distance from the hinges, from the axis of rotation, and that distance is what we're going to call the lever arm. So this distance between the hinges to where the force is applied is called the lever arm. Okay? It's how far that force is being applied from the axis of rotation. And the longer that lever arm is, I'm going to show you guys, hopefully, the easier it is to start that door rotating, or whatever object you are acting on. Okay, so let's just define that really quickly. Okay, so the lever arm the lever arm is the distance between the axis of rotation and the point where the forces are being applied. Okay, so it's just the distance I drew in that diagram up there. And one thing I also wanted to point out, which I think you guys also know intuitively, is that only forces perpendicular to the lever arm will cause an object to rotate. Let me write that down and then I'll show you. Only forces perpendicular to the lever arm will rotate an object. Okay, let me show you what I mean by that, and then I will draw a picture of it just to reinforce that. Okay, so remember, here's our door again. Okay, our door, we have our lever arm defined. It's the width of the door. Okay. The force I'm going to apply to open it is perpendicular to the lever arm. So the lever arm is going this way, and the force I'm going to apply is pushing it in. Okay. So that's going to open the door. If I applied the same force along the direction of the door, let's see, some of you guys can't see me, but okay, if I'm pushing in, okay, I can actually push with as much force as I want here. Oh, good, we got up there, so I can push. I'm going outside the room. Okay, so I'm pushing along, but I'm pushing in the same direction as the lever arm. That does absolutely nothing to rotate this door. Okay? It's only forces that are being applied perpendicular to the lever arm that will rotate an object. Okay, so let me draw a picture of that if you, in case you couldn't see that. Okay, so here's our door once again. Here's our hinge, so it's defined the axis of rotation. Along that hinge, here is our lever arm. Okay, so what I just said was force applied perpendicular to that lever arm is going to rotate that door, right? Force applied along the lever arm is not going to rotate that door. No. Unhappy face. No rotation. Okay. Only the forces applied perpendicular to the lever arm are going to cause a rotation of that object. Okay, so let's look at torques in a little bit more detail. What I've got here is a fulcrum, which is just a balanced arm. Let's see. Yeah. Can you zoom in on this? There we go. Okay, thanks. So here we just have a bar which is balanced around its center. Okay. So right now, this is, all the torques on this is balanced. It's not trying to rotate. Okay? If I push down at one end, so I'll have a lever arm, and I'll have a force that's pushing it down, so I'm applying a torque, which is rotating it. Okay? So this thing is free to rotate, but in its natural state here, all those torques are balanced. So the axis of rotation is right here through the middle, okay? And this is the rotational direction around here. Okay, so let's put some weights on here, and let's explore a little bit the concept of lever arms. So I'm going to start by just adding a single weight on one side. So if I'm adding that weight on there, then I've got the weight of that object pulling down. It's got a lever arm, which is this distance. And so it is acting to rotate this bar. And so it's applying a force over a lever arm. It's applying a torque. Now let's take the same mass. Okay? Let's hang it from the same distance on the other side. So in this case, the forces are the same. The forces acting on both sides are the weight of the two masses. And the lever arms are the same. Okay? So these are applying equal torques on this, but in opposite directions. One of them is trying to pull this side down, the other one's trying to pull this side down. And so they are balanced torques. And in this case, there is no net torque on this, so it doesn't want to rotate. Okay? So equal weights, different lever arms. Equal weights, same lever arms. So these are balancing out the torques on this. Okay, so let's play around with this a little bit. So let's take this mass and move it out to the right. We're going to double the distance on it, so it is twice as far from the rotation axis from this one. So it's going to have the same force still as this mass, but twice the lever arm. Okay? And if we do that, see they're not balanced again, right? There are equal forces on both sides, but the torques are not the same because this one has a longer lever arm. So it's applying more of a torque, and it's winning out. Okay? They're no longer balanced, and there's a net torque that is pulling it down onto the side. Now, just to show you that it would be balanced if I do that, let's move this back out to the same distance. Okay, so now the lever arms are the same, the weights are the same, and all the torques are balanced again. Okay, so there's no net torque on this, so it's not being accelerated. It's just rocking because I gave it a little bit of motion there. Okay, so all the torques are balanced. Okay, so let's go back and put this in the original location here. Okay. So this lever arm is twice this lever arm. Okay. Remember, that's unbalanced. There's a stronger torque on this side. But now let's change the mass. So this one has twice the lever arm. Let's change the weight on this side so we now have twice the weight. Okay, so it's twice the weight, half the lever arm. And you can see these are back balanced again. Okay. This is how you make mobiles, right? When you're a kid. So here we have half of the weight, so half the force, but twice the lever arm, and that's balanced with, over here, what is half of the lever arm, but twice the weight. Right. So that's telling us the torque, okay, that is trying to rotate this is proportional directly to both the force and the lever arm. Okay. So if you double the lever arm, it's going to double the torque. If you double the weight or double the force, it doubles the torque. Okay. So we can do this, we can do this ad nauseum. We could do 3 on this side. Okay. That's clearly not going to be balanced unless we move this one out to a longer distance. I think I have to be a little more clever about that. There we go. Is that right? No, here we go. Okay, so here we've got 3 times the force, okay? So three of these weights, but 1/3 of the lever arm, okay, balanced against what's 3 times as long a lever arm, but 1/3 of the force. Okay, so torque. Torque is a direct product of the lever arm and the force that is acting on it. So let's write that down. So torque is our analogy to force, but in order to rotate an object, you have to take into account the length of the lever arm. So our torque is equal to the lever arm times the force, okay? So if you double the force on one side, you have to half the lever arm in order to get the same amount of torque, and vice versa. Okay, so torque also has a direction, right? So this mass is trying to pull down the fulcrum in this direction. Okay? We define the torque using the right-hand rule as well. Okay? This torque is trying to rotate the object in this direction, so we define the torque as being along the thumb. Okay? So that is the direction of the torque. It's also the direction of the angular acceleration that's being imparted by this one. Likewise, this force is trying to rotate it in this direction, okay, which means that the torque is directed back along this direction. Okay. So torque depends on the lever arm and the amount of force. So even if the forces are balanced on an object, if they're acting with different lever arms, then they can still impart a rotation to it. So you have to keep into account for rotational motion, not just the magnitudes of the forces, but where they are acting. So how far from the rotation axis the forces are acting. Okay, so let's, the other concept that we introduced over here, which we want to talk about now, is rotational mass. Okay, remember regular mass is how hard it is to, it's a measure of the inertia, how hard it is to accelerate an object. So rotational mass is the same. It's the measure of the rotational inertia, how hard it is to rotate an object. So this measures rotational inertia. Okay, so there is part of rotational mass which is very intuitive, and part of it which is not intuitive, at least not to me. So the intuitive part is that more massive objects are harder to rotate. Okay. I think that's pretty intuitive. The more mass an object has, the harder it is going to be for you to start that object rotating. The unintuitive part is that the further the mass is from the rotation axis, the harder it is to rotate as well. Let me write that down and then we'll show examples of that. So the further the mass is from the axis of rotation, the harder it is to rotate. Okay, so I need 2 volunteers for this. one of which is not subject to motion sickness. Do you get motion sickness? Okay, come on down. Let's see, let's pick one more. You can be my rotator. Come on down. Okay. Don't be scared. What's your name? Francesca. So Francesca is our rotational mass. Go ahead and sit in the chair. Thank you. And what's your name? Virginia. Virginia is our torque for the day. So Francesca is our rotational mass. Yeah, let's thank him in advance. And Virginia is our torque. Okay, so to make this a little bit more instructive, we are going to give Francesca these two weights. Okay, so hold those right in your lap right now. Okay, so are you sure you don't get motion sickness? I'd totally hurl on this. Okay, so Virginia, I want you to start rotating her, okay? So you're going to be applying a force, okay? How do you want to apply that force? You want to be doing it with a lever arm, right? Okay. Let's interesting. Okay, so Francesca has a rotational mass. Okay, the weights are adding to that. And we can see how fast she can spin her. It's about once per second, right? The rotation there. Okay, let's slow her down a little bit. Are you getting sick? No. Oh, good. Okay, we're going to slow you down a little bit. Okay, so now, we're not done yet. Poor Francesca. Okay, so we're going to take our rotational mass and we're going to redistribute that by having Francesca hold her arms out as far as she can. Can you hold those weights out? It's pretty hard to hold those out, right? Okay, so now here comes our torque, Virginia. Okay, Virginia, try to spin her up the same. Okay, Francesca has the same mass, okay, but she does not have the same rotational mass because the mass is being distributed further from the rotation axis. Okay. She's harder to spin, right? Is she a lot harder to spin? Yeah, you can see she's getting nowhere near 1 spins per second like she was before. Okay, Francesca, okay, let's not spin her anymore. But Francesca, can you do me one favor, which is to pull your arms in. Okay, now pull them back out. Slow down, excellent. Okay, you can see that her mass did not change during that whole encounter, but her rotational mass changed quite significantly. Okay, thank you, Francesca. Here, let me take those. Yeah, let's thank Francesca and Virginia. Okay, so the point I wanted to make with that was that, so when she was holding those dumbbells out at her arm's length, so the total mass of her plus those weights wasn't changing, but the mass was being distributed much further from the rotation axis than when she held those masses in, which was changing her rotational mass. Right? We'll see, actually, not in a week from today, next Tuesday, what was actually happening when she was pulling them in and out. But she was basically changing her rotational mass, which was changing her velocity because of angular momentum, which we're not talking about today. We'll be talking about that next week. Okay, so let's define exactly what rotational mass is. Okay, rotational mass is similar to torque in that it depends not just on how much mass is there, but how far it is from the axis of rotation. Okay? Rotational mass is specifically defined as the mass of an object times the square of the distance. from the axis of rotation. Okay, it goes as a square of the distance. So what that means is if you have a mass and you're trying to rotate it, let's say you have a mass on a little light stick and you're trying to move it in a circle, right? If you move that mass out by twice the distance, so you move it twice as far from the rotation axis, then it becomes 4 times harder to accelerate. Okay? Rotational mass goes as a square of the distance from the axis of rotation. So that's why when Francesca took those masses and she moved them from here close in to far out, the fact they went as a square of the distance, that distance was changing really dramatically, meant that she was adding a lot of rotational mass to that system. Okay, so she was much harder to rotate. Okay, so you can do a little example of this if you want. Let's see. I've got a meter stick. You can do this with your pens. You can do it with a ruler when you get back. Okay? You're just going to shake it. Okay? If you take your pen and you hold it in the middle, okay? You can feel how easy it is to shake it. You're basically just rotating it. You're imparting a torque. Okay? Now, if you try to do that from the end, we're taking the mass of the meter stick and we're moving it further from the axis of rotation. Okay? It's a lot harder to make it move. Okay? This is much more dramatic if you do it with like a baseball bat, right? Or a tennis racket. You can try this when you get home. Okay? You're moving it here, this sort of the minimum distance all the mass can be from the axis of rotation. Okay? From here, it is maximum. Actually, this is the minimum, if we do it this way. Woo, it's really easy to rotate along that direction, right? It's much harder to rotate along this direction, and it's really hard to rotate if you got it from the end like this. Okay? Same mass, it's just being distributed further and further away from the axis of rotation. Okay, so you, yeah, try that on a heavy object when you get home, especially a baseball bat's a good one. Last concept I want to introduce, I just want to tell you, because I think it's pretty obvious. If you're applying a torque to an object and you start it spinning, you're doing work on that object. I think that's obvious. It's spinning up, it's getting kinetic energy. So a torque acting over to rotate an object is doing work on that object and spinning it up. It's imparting kinetic energy to it. If you apply a torque on an object and it's not rotating, okay, like I'm applying a torque onto this table by lifting it up, okay, it's not moving, I'm not doing any work on it. Okay? So just like a force has to act on a displacement in order to do work, a torque has to actually rotate an object in order to impart work to it. But if it does rotate an object, then it's transferring energy to it, it's doing work. Okay, so 2 more concepts I want to introduce today. One is the center of mass of an object, and the other is the center of gravity. And there's a little distinction between them, but here on the surface of the Earth, they are the same thing. So we're not going to be too much of a stickler about this. Okay, so here I have an object. Every object has a center of mass. Okay. I could take this object and I can rotate it about any point. I can rotate it about this end. Okay, I can rotate it around this end. I can rotate it around the center. Okay. In that case, I'm defining an axis of rotation for this point. Okay. But this object also has a center of mass. Okay. And the point about the center of mass is if this thing is free to rotate on its own, it's always going to rotate around the center of mass. Okay? So if I take this object and I just throw it up, okay, I'm no longer forcing an axis on it. You might want to pan back for this part way. Okay, I'm going to be throwing this up in the air. So if I just throw this up, okay, this object is going to start rotate. Well, it doesn't have to. I could throw it up like this. Okay, and it's not rotating. Okay? But if I do give it some rotation, okay, it's always going to rotate around the center of the mass. And that's just the average position of all the mass that's distributed on this. You can see why I do physics. Okay. My baseball career ended very early. Okay. Ow, where did that go? There we go. Okay. When I give this just free motion like that, okay, it's got translational motion, it's moving up and down, but it's also got rotational motion. But the rotational motion is always going to be around the center of mass. Right? So let's see, Maxwell, can you come up for 1 second? Hope you're a better catch than I am. You doubt it. Okay, so we're going to play catch with this just like you would a normal baseball. It's just that this thing can rotate, right? And as it moves, it undergoes translational motion. And that translational motion does not change at all. It's just that it follows a trajectory. That trajectory is defined by the center of mass. Okay? But it can also rotate around that center of mass. So it's got the translational motion, which is just following the center of mass, and then the rotation around the center of mass. So I'm not sure if that's going to, let me take this off. Are you ready? Okay, first off, if we throw it without any rotation, there you go. The center of mass is just going to follow a trajectory, just like if it were just a normal ball. There you go. Are you ready for this one? Let me put this back on. Okay, so now if we give it some rotation, okay, I'm going to be spinning it. It's got the rotation, but that's completely around the center of mass, and then the center of mass is just following the same trajectory it would have normally. So if you look at this video again and slow it down, yeah, I think this is the last rip. Oh, okay. You'll see that that center of mass point just moves in a very smooth arc back and forth, independently of how fast this thing is rotating. I think that's good before we put our eye out. Thanks, Maxwell. Okay, so that's the center of mass. If an object is free to rotate without forcing an axis of rotation, it'll always rotate around the center of mass of the object. Let's see, I don't know, do I have a good example here? I guess a wheel is a good example. If you imagine this was just a rim, a hula hoop without any spokes on it, the center of mass for this hula hoop is in the middle. Okay? The center of mass of an object doesn't actually have to be physically located in the object. Okay? It can be, it's just a point in space, which is the average position of it. Likewise, if we had a, if I can do a drawing of this, imagine that's a boomerang. Okay, there's a boomerang. Okay? When you throw it, it will rotate around that point, and the center of mass is sitting out here in space somewhere. And that is the point about which it will rotate if you throw it freely. Okay, that's center of mass. Center of gravity is a little different concept, but it turns out on the surface of the Earth to be the same position. And that is when you're calculating the torque of an object, that is effectively where gravity is acting. And let me write this one down. So this is the center of gravity. Okay. And the center of gravity is when you're calculating torques. Okay, the weight of an object acts as if it's being applied at the center of gravity. Let me write that down, then I'll show you an example. Weight of the object act as if applied at the center of gravity. Okay, so let me draw you some pictures of that, which hopefully will make that a little bit clearer. Okay, first I'll show you intuitively, and then we'll draw pictures of that. So here we have our meter stick again. The center of gravity is, in this case, the same as the center of mass. It's right at the center. Okay? which means if I am supporting this, if I'm defining the axis of rotation about the center, okay, even though this meter stick still has weight, that weight is effectively acting at the center of gravity point, and which is, since there's no lever arm, that means there's zero torque. So this thing is not rotating, okay? It's balanced. So for counterexample, if I try to hold it at one end, it's really hard, okay? Because now the center of gravity is at this point, and the lever arm is half of this, okay? So it's trying to rotate it downwards, okay? That's pretty intuitive, right? Likewise, if I hold it at the other end, okay, the weight of this meter stick is effectively acting at the middle, okay? Here's the lever arm, there's a torque, and it's trying, there's a force, and it's playing a torque which is trying to rotate it downwards in the opposite direction. Okay? So the weight of this object is effectively acting like a force that's being applied at the center of gravity. So when you're calculating the torque on an object just from the fact that it has a weight itself, not from an outside force, okay, we know where the lever arm is for an outside force, but for the weight of the object itself, it's effectively acting at the center of gravity. On the surface of the Earth, that's the same as the center of mass. Okay? If you're up in space, it's a little different story, but on the surface of the Earth, you can take those as the same. So let's draw just the pictures of that real fast. So here's there's our meter stick. Okay? Here's our support at one end, so that's the support. And in this case, when we're holding it from one end, the weight is effectively acting here in the center of the stick. That's the center of gravity for that object. There is the lever arm. Okay. And if we're looking at the torque is trying to rotate it in this direction, so the torque would be pointed into the board in that configuration. Okay. If we have that right in the middle, so the weight is acting straight downwards, then there is no lever arm, because the weight is effectively acting right at the point of rotation. So there's no lever arm, which means there's no torque, which means that it's completely balanced. And then the final example is if we move that support over to the right-hand side. Here is the lever arm again. The weight is still acting in the middle. Okay. In this case, it's trying to rotate that meter stick down, which means that the torque is pointing out of the board. It's in the opposite direction from the case on the other side. Okay, so here's an example of center of gravity that I think is kind of interesting, which is, I'll write it here. This is called a corbelled arch. It is found in ancient architecture all over the world, and it's basically a trick using center of gravity to create, or manipulating center of gravities to create arches over doorways. So let me show you how this is done. So here's our bricks, okay? And we want to make a doorway here, okay, through this section. So we want to build an arch over that. And the simplest way to do that is just to take advantage of the center of gravity for these bricks. So here's a brick, and you can imagine if so pretend this is the top of our doorway here. If I'm pushing this out, right, at some point, if I get the center of gravity over the edge of that support, it's going to fall, right? So that is the maximum I can push out that brick before it falls. But in that position, it's perfectly balanced, right? And so it's structurally sound. It's not trying to fall over. Now, that's not much of an arch. So we probably want to add on to that. So you can imagine you're going to start putting another brick on top of that, right? Okay, if it goes straight up, then it's not going to change. The center of gravity is still being supported by the edge. But if we start moving that out to try to create more of an arch, it's going to fall over, right? So now let's think about this from the two bricks separately. So if I add another brick onto this, okay, I'm going to be putting a torque that wants to rotate it, right? So I got a torque that's rotating it down. Okay? And so I'm going to have to slide that back over a little bit so that its own weight is balancing that torque. Okay? So let's start building these. Okay? The top brick can basically go out to half of its length, okay, because it doesn't have any other torques acting on it. So that one can go out halfway before it becomes unstable. Okay? The bottom one's not, now this one's not going to go out nearly as far because the top one is adding a torque on it as well. Okay? So we're balancing the center of gravity for the two of these. Okay? But it's a stable situation, it's not going to fall. Okay? You can see we've started building a little arch here. So what we really want to do that is for more and more bricks. Okay? So, but each one you add and move over is going to be applying another torque to the ones below it. And so you're going to have to, you can't move them out as far. So the top one can always go out about halfway. Okay? Turns out the next one can only go out about a quarter of its length before it becomes unstable. Okay, that's sort of balanced. The next one, this is now getting nerve-wracking, can go out, so this is a half, this is a fourth, the next one actually can go out a sixth. You can imagine that the ancient builders were very patient people. Okay? And the next one can go out an eighth. If you keep going, it goes up a 10th, a 12th, a 14th. You can try to do the math on that if you want to do a little like puzzle this weekend. But at some point, there's sort of diminishing returns. If you're adding, 1/50th of a brick length to your arch, you're not adding much of an effect on it. But you can start imagining that there is a nice stable situation, and you build another one coming from the other direction, okay, and you've got a nice stable arch that you built. So this is called a corbelled arch, adjusting the center of gravities for these objects. And it's actually found in ancient architecture all over the world. So a lot of different people's figured out how to play with the center of gravities for these, at least intuitively, when they were building stuff. Okay, so that's actually all I've got for today. And I think we'll pick up there on Thursday.